All right. Good morning, everyone. Thank you to those of you that are able to join me. The SEI completion rate is currently at a 77%. So thank you to everyone who has completed it. It is highly valuable. I really appreciate any amount of time you can give. So we just need 3% more of the class, which is, let's see, 2 or 3 times. How many students are there? 240, I think. So we just need like 7 more students to complete the SEI. Well, hopefully everyone completes it, but we need at least 7 more students to complete the SEI. And everyone will get extra credit on the final exam. All right. Are there any questions before we get started? Okay. So what I will request is that if you do need to ask questions, I want you to, that's great. But I'll ask that you either put it into the chat or raise your hand, doing the little hand icon, and then you can bring yourself off mute. This is, again, just to make sure that we aren't all talking on top of each other so that we can have a, nice, good dialogue. We won't have time to go through the entire exam. So I would like it if you could let me know by putting into the chat which questions you would like to make sure that we focus on. And I'll try to make sure that we get to every single one of those questions. Rachel, you were on it. You were ready for that. I love it. Kind of seems like the second half of the exam is what we're looking at. So awesome. So you probably noticed that a lot of the questions are actually kind of similar to what you've already seen. Oh, one other thing to point out, there was a weird technology hates me. Microsoft Word had a weird thing where it changed my heading on the first 2 pages, but nowhere else. This is the final exam. So like if you look everywhere else, it does say final exam. For some reason, the first 2 pages just had a different heading. The note that is given saying that we're going to assume all reagents are in excess on the entire exam unless told otherwise. That is going to be true for your exam as well. So it'll be the same setup, same kind of format and everything. All right. So kind of looks like we want to work backwards because it's a lot of high numbers. So I'm going to start at the end and kind of work backwards. So 28A we're wanting. So yeah, absolutely. All right. So yeah, this is going to be our conjugate addition. So when we look at this, the thing that we have to make sure that we're doing is that we are following the instructions always. That's the most important. So actually, I know the instructions are long, but let's pull out the key parts of it. So we're trying to provide a reasonable mechanism, cool, where we are making the given product. So we got to make sure that we are making these products, whether they are the major or not, doesn't matter. We are making those products. And we're only using the given starting material and reagents. You only need to show the mechanism producing the given stereoisomer. Do not add any reagents. This is not a synthesis part. This is the mechanism part. We're looking for the curved arrows using the reagents provided. We're going to include all relevant lone pairs, formal charges, curved arrows, all reactionary equilibrium arrows, so the forward or equilibrium, intermediates, inorganic, and organic byproducts. We cannot use PT for proton transfer, nor B as a generic base. So we must use the best base in solution. All right. So the only thing that was different from our normal every other exam mechanism instructions is that I'm asking you to make this specific stereoisomer because that's the only one that's chiral. All right. So starting out, we see that we have this conjugated diene and we see the BRCl. This reagent is going to be going through an anti-addition. So two things tell me that I'm doing an anti-addition mechanism. One, it looks like when we had Br2 or Cl2, right? So that reagent always did our anti-addition. But I also have the product helping indicate that to me, because I'm looking to see, where do I see these elements? And the fact that I only have one equivalent means I get one bromine, one chlorine. So the reagent is putting these on my starting material. Like, that's how I'm getting it into my product. So we got to make sure that, you know, we're showing the anti-mechanism in order to get that trans product in the end on the trans ring. So to get started, we want to start from the alkene. Normally, you would start from either one and it wouldn't matter, because they both are tri-substituted alkenes, right? So this top one has, there are the 3 groups for the top double bond. Here are the 3 groups for the bottom. So they're equally as electron rich. In this case, though, we want to make this thing. So we're going to start from the top double bond. Also, I apologize in advance for the, actually, I need to close that blind a little bit. It's actually glaring in my eyes. So our curved arrow. Okay, the curved arrow, that didn't do anything. That is, okay, whatever. I'm just glad we have sunshine. Curved arrow is going to start at the double bond and then go to the more electrophilic side, because remember that this is my nucleophile, this is my electrophile. So I also can pay attention to the fact that the chlorine is the one that ends up on the more substituted side. So that also tells me that I need to make sure that chlorine is the one that's going to open the intermediate. So besides the fact that, like, the product is telling me which molecule I need to use, or which atom, remember that our electronegativity increases as we get closer to fluorine. So on the periodic table, it is fluorine, chlorine, bromine, iodine. So that means we are increasing the electronegativity as we get closer to fluorine. So the chlorine is the more electronegative atom, bromine is the less, making the bromine the more electrophilic side. So we're going to start at the pi bond, go to the electrophilic atom in that molecule, and then we're going to break the bromine chlorine bond, give the electrons to chlorine. And then remember that where this deviates from just our normal HCl, you know, strong acid mechanism, is that bromine has a lone pair of electrons. That's going to bite back down on the more substituted side, because that's going to be our more electrophilic side. So that's the side that the bromine is going to close back down on top of it. So that's why these are the set curved arrows. It had to be these ones going to these exact sites. And you could use either a forward or equilibrium arrow. It doesn't actually matter here. Technically, equilibrium is more correct, but I accept a forward as well. And because I want bromine on the wedge, and I'm showing the attachment of bromine, I need to make sure that that bromonium ion is on the wedge. So I need that bromine in a 3-membered ring with a positive charge that's going to push this methyl onto the dash. If you get a wedge, you get a dash. So that methyl goes onto the dash, and everything else stays exactly the same. So then the next step is just having that chloride attack the more substituted side to pop open the ring. So when this chlorine is coming from the dash, because remember that bromonium ion intermediate, that's blocking that top face. So your nucleophile has to come from the opposite side in that SM1 type reaction. So it's going to come from the opposite side. That's what's forcing the chlorine onto the dash. And then the methyl just has to deal with it, which gets us to our product. The other product, if you wanted to see, because this is our 1-2 addition product, which this is the major at 0 degrees Celsius, because that's asking for the kinetic product. and 1,2 addition is the major product at colder temperatures. So our thermodynamic product is going to be the 1,4 addition, because that's going to lead to the more stable alkene. So if this was at higher temperatures, then what we would have needed to do is, instead of having that chloride attack right away, instead we have this double bond shift over, oops, and that's what pops open the ring, right? So then this is in equilibrium. Again, you could use a forward arrow or equilibrium, whichever one makes you happier, but it's important to note this is not resonance. Even though it's kind of acting like resonance, we're treating it very similar to how we treated our like the carbocations in resonance that formed with our conjugate addition. This is not actually resonance because we're breaking bonds. So remember that resonance is only moving electrons through p orbitals. We are not actually changing connectivity. Because I'm changing connectivity, this is equilibrium, not resonance. But you could use a forward arrow if you wanted to use a forward arrow here, that'd be fine. So that gets the bromine on the wedge. I now remove that dash on the methyl because now that methyl is a part of the double bond and we don't show wedges and dashes on double bonds. So then now the chloride would attack. Ooh, come back here. The chloride would attack. Again, forward or equilibrium arrows, whichever one makes you happier. And because it's a carbocation, we're going to get the mixture of wedge and dash. So it would create those diastereomers as the products. So this would be this plus your enantiomer are the major products for the 1,4 addition, which is our thermodynamic product. Any questions about 28A? Okay, cool. All right, so next one's 27. Ah, yes, all of our predict the products. Yeah, I can't do alphabet, so I'm just gonna do them as I see them. Okay, so let's start with X because I see that one showing up a couple of times. So for X is again our conjugate addition. So it makes sense that we're seeing this. So it's a conjugate addition because, and I know it's conjugated because it's that double, single, double. And to clarify, for conjugate systems, it doesn't have to be a double bond. It could be a triple bond. It's the fact that you have pi bond, no pi bond, pi bond. That's what's actually making it conjugated. It's just normally we're looking at it as a conjugate diene, so it's normally double, single, double. But triple bonds also can be in conjugation. So with our hydrochloric acid, one equivalent is telling me that I'm only going to add one hydrogen and one chlorine. That's what the one equivalent tells me. So I'm not going to keep reacting with every pi bond. I'm only going to do one addition. Seeing that I am at 60 degrees, that tells me that I'm going to do the 1,4 addition because that is my thermodynamic product. So when I look at this, there's 1, 2, 3, 4. So I need to end up with my pi bond in the middle. So if this is 1, 2, 3, 4, the double bond ends up between 2 and 3. The hydrogen went on to carbon 1. The chlorine goes on to carbon 4. And you could either show it as the wedge and dash, or show it as just a straight line showing that you recognize the mixture. And this hydrogen can be implicit. That's totally fine. The mechanism is going to be that carbocation mechanism because it's a strong acid. So we're going to start from, and actually it doesn't matter which one you start from. It could have been either double bond because they're, again, both tri-substituted, so they're equally as electron rich. So I need to actually redraw it because I don't see the bond. I need to use equilibrium arrows here if I'm drawing my mechanism, although this question doesn't ask for mechanism, but I would need to make sure that I have the equilibrium arrows here because this is strong acid, and I want you to remember every acid-base chemistry or every single acid-base reaction is highly reversible. So that's why it's really important to me that you keep using the equilibrium arrows there. Right. So then now we get a true resonance arrow because we're just moving those pi electrons. We're not actually breaking any sigma bonds. But then the chloride attacks. So because it's the carbocation mechanism, that's how I know that I have racemization. The high temperature told me it's a 1,4 addition for the thermodynamic product, making sure that I get my tetra-substituted double bond. And that's how I knew to get to that product. All right, any questions about X? I think I saw W, yeah. All right, cool. So remember, on the entire exam, unless told otherwise, like we were here, like here it says one equivalent, which by the way, if it didn't say one equivalent, if it said excess, then we would get a mixture of products because that double bond could react again. So then you would actually have two products to draw. Because when you do that second reaction, the double bond is, or the carbocation would be positively charged, whether it's, what am I saying? The carbocation would be tertiary no matter what. It's always positively charged. It's a carbocation. But it would be tri-substituted. It would be tertiary. So it's going to be stable either side. So you could argue that this one might be slightly more formed. So like maybe it's like 55-45 or something. Like you might get a little bit more of this because this is going to be inductively withdrawing, which might destabilize that positive charge being right next to it. But I don't know. I would expect you to draw both of them if it was in excess. Yes, the 1, 2, and 1, 4 additions, that's only with our conjugated systems. That was the only time that we had to worry about that difference. And it's because that pi bond is right next door. So back to W. Because it is in excess, that means that we're going to react with absolutely everything that we can. Anything that can react will react. So my lithium aluminum hydride, that is a reductant and a nucleophile and a strong base. That's how that reagent reacts. So whenever we were reacting LAH, that was the one that was able to reduce every single carbonyl. Every carbonyl, carboxylic acid, whatever, didn't matter. Because some of our other reagents could do other carbonyls, but not the carboxylic acid. Lithium aluminum hydride does it all. So that is going to turn absolutely every single carbonyl into the alcohol. And it's going to turn it into the either primary or secondary alcohols. So what we're going to do is in step 1, we end up with those 2 alkoxides, which would have been coordinated to an aluminum. So might as well just draw it in. So that would have been the product of step 1. We normally used an acid workup after the lithium aluminum hydride because that was the strong base. So we couldn't have any sort of acidic protons because it acted as a base, which is the difference with LAH is that if it's in massive excess, it can do the deprotonation and then keep reducing. Whereas like our Grignard is going to do the deprotonation and then stop. It's not strong enough to actually react with the carboxylate. Whereas lithium aluminum hydride does it all. So I get to these O minuses, which are now strong nucleophile, strong base. So then, which actually I'm gonna go back to just showing it as an O minus, because I think it'll make it a little bit easier to think about the reactivity. So that alkoxide, strong nucleophile, strong base. Step 2, instead of it being an acid workup, I'm giving you an electrophile. So this is that Williamson ether synthesis. Which is we're doing an SN2 reaction. So whether you know it's the Williamson ether doesn't really matter, but it's just the fact that you have a really strong nucleophile that's going to do SN2 in order to make an ether. So I'm going to have, and again, it's in excess, so every single one of them reacts, that both of them will do that SN2 reaction. So we alkylate both oxygens to get our 2 ethers. A lot of students made a mistake for this question where they didn't pay attention to how many carbons they had. So either they added extra carbons, removed carbons, or they tried to leave this oxygen on. But remember with LAH, it takes all of this, like it essentially is removing that carbonyl to give you the primary alcohol. It turns a carboxylic acid into primary alcohol. Right. Any questions about W? I don't see Y or Z. How about U or V? Yeah, U comes up a couple times. All right. Yeah, so this is the hard synthesis question that we did on our last exam. So instead of it being predict the reagents, I'm now giving you the reagents and asking you to predict the products. So for this one, we'll just work through it again. Strong acid, protonate something. My most basic site is going to be this oxygen. It has 2 electron donating groups, so it's going to be a good Lewis base or Bronsted base. So right now, I essentially made a really good leaving group. So I can either break it this way to lose tert-butanol, or I can break it this way. So in order to know which one is my leaving group, which one's acting like that oxonium ion, I need to think about the carbocation that I'm going to form. So if I break it this way, I'm trying to make a vinylic carbocation. I'm putting a carbocation on the double bond, not next to it, on it. That is not stable. Next to a double bond, great. We get conjugation, we get resonance. That's so happy. On it, no. That is a very unhappy carbocation. So we're going to avoid putting a carbocation on sp2 hybridized carbon. So that means that our only option is to break the bond that way. So now I have my methanol with a carbocation. This is my weak nucleophile, weak base, which, I mean, we kind of already knew that we were doing SN1, but I guess we didn't necessarily know. That's fair. If you anticipate it, so if you didn't draw this product, so I probably should have made this cold to reinforce that I wanted you to do SM1, not E1. Since it's room temperature, then the E1 might predominate a little bit. So yeah, I would have, I don't think anyone did it, but I would have accepted it either way. So I can have the methanol attack in to do SN1, or it could deprotonate and do E1. My enolate, or my enol, remember that enol readily tautomerizes to become the carbonyl. So I was looking for that ketone product. I wanted to see that students remembered that enolization can occur. So that was the point for that side of it. And then the second product was I was looking for you to recognize either SM1 or E1. So if you did SM1, it would have looked like that. If you did E1, it would have looked like this. I don't think any students actually drew the E1 product. Most students weren't sure what to do with it and actually left it blank. But all right. Any questions about you? Was V anywhere? No. S or T? Nope. Q or R? R, yes. R shows up a couple times too. All right, cool. So I am seeing my halogen with an alkene. I'm going to do an alkene addition. This is going to be an addition reaction. I see that with the Br2, with that halogen, the diatomic molecule, that is going to be the anti-addition. And then we need to remember that in protic solvent, that solvent is the better nucleophile because there's so much more of it than the halogen that's going to form, that it is going to be your nucleophile. So usually this reaction is going to be run with Cl2 or Br2. And again, it's because with chlorine, we're getting that tight solvent shell, so chloride could never act as a nucleophile. But my major product is still going to be where the solvent acts as the nucleophile to open up the bromonium ion, because there's just so much more of it. So it's one, slowing down the bromide, but then there's just a massive excess of that protic solvent that is what's going to open up that bromonium ion. So we're going to have alkene attacks the bromine, it pops open, double bond, bites back, or sorry, the bromine bites back down. We get that bromonium ion intermediate, and then ethanol opens the ring on the more substituted side to give us our two products, and can attack from the wedge or the dash, because this, it would be anti. So actually, let me clarify this. So if this was a wedge, then your OET would be a dash, but that bromine could have been on the dash. So if the bromine was on the dash, then your OET is on the wedge. Or you could draw because this is just a mixture of enantiomers, you can draw them with the straight lines. What am I doing? I deleted a carbon. Whoops. I'm like, how are they on the same carbon? That doesn't make any sense. All right. So if this was the wedged bromine, there's my dashed OET. If this is a dashed bromine, then this is a wedged OET. And so then the point that I'm making is that this is the only chiral carbon. So what I was saying is still a true statement, but it just, the bromine was in the wrong spot. I lost a carbon. Because this is 1, 2, 3, 4, 5. I need to make sure I have 5 carbons. Yeah, now we're good. So then, because this top carbon is not a chiral center, I don't need to have wedges and dashes there. So that's why it would be okay to just represent it with all wedges and dashes, because it really is just the mixture of enantiomers, because this top carbon is not chiral. So I don't need wedges and dashes there. Any questions about R? O or P? No. M or N? No. K? Yes. All right. So I see my hydrochloric acid with an alkene. This is my strong acid. That tells me I'm doing my carbocation addition. Strong acid, protonate something. So I'm going to be protonating that double bond. Remember that when you go through that carbocation mechanism, you must make your most stable carbocation before you do anything else. Always. Every time you make a carbocation, stop, check to see if you could have rearrangement, if there's any other way to make a more stable carbocation. Here, I can do an alkyl shift. To go from my secondary to my tertiary carbocation. And now my nucleophile can attack. Well, comparing chloride to methanol, although chlorine is normally a good nucleophile, this is my protic solvent. In protic solvent, chloride is not a nucleophile because of that tight solvent shell. Chloride is that tight solvent shell. So in that case, methanol is actually my best nucleophile. So methanol is what would attack in. If we were doing SM1, but we're actually doing would have been a mixture of SM1 and E1. Wow, I'm sorry, summer students, I was inconsistent on this. The problem is that the reality is that you do get a lot of the SM1 product. So it probably would have been better off to show, so this is the SM1. And then looking at this E1, because this is room temperature and because of the trend that I told you to oversimplify it, if you drew the E1, it would have had to have been this E1 product because it needed to be the Zatsev and E. In this case, there's no stereochemistry, but it needs to be the most substituted alkene. So in this case, I should have accepted either product, the SM1 or E1. But because it was room temperature, I should have expected you to do E1 because of the chart that I gave you. Okay. Any questions about K? Yeah, so iodine is the only one that is a better nucleophile in protic solvent. So if you see iodide, so that was why on the last exam we had that it was like the OH with HI and methanol. Iodine was the better nucleophile. Because iodide is a large atom, so it does not get a tight solvent shell, and it's now negatively charged, so it is going to outcompete that methanol. It remains the best nucleophile in solution. Any other questions about that one? Okay. Actually, did I get through all of them? No. H. Still need to do H on 27. All right, so that's this one. Yeah. Okay. So we got to remember what this thing is. That is my diazomethane. So if you're unsure, draw out the Lewis structure. So that is the major resonance form. We also have the minor, which is going to be the more reactive one. And so in heat, what we're going to do is we're going to have, so all heat really does is break bonds. Like that's the whole point of heat really is just, it's energy to break bonds. It's energy in to cleave a bond. So that heat is going to break that bond. And so then it's going to give the electrons to the more electronegative atom, nitrogen. And so then you're going to end up with, and this has to be a true forward arrow, your carbene, because you're making nitrogen gas. That's why it has to be a forward arrow. You're making nitrogen gas. So it literally bubbles out a solution. And so then that carbene does your syn addition. So we're going to end up with a cyclopropane. And the mechanism is literally alkene attacks carbon, lone pair attacks back down, and it just sits on top. And it would have been both wedges and dashes, although there is no stereochemistry here, so it doesn't really matter because it's all symmetrical. So yeah, it just is cyclopropane. So the carbenes are the ways to make our little triangles, or cyclopropanes. So a big part of 27 is just, do you know what the reagents do? Do you know which mechanism you need to be doing? And then draw the product. Okay. I think that's everything for 27. Are there any others on 27 that you want to go over before we move off 27? When studying for the predictive products, it really just is making sure that you can organize the reagents. So like how I go through and I did like my lithium aluminum hydride, that is a reductant nucleophile base. I know how it acts. Strong acid, that is the it's going to protonate things. When I saw methanol, I know it's a weak nucleophile, weak base. The halogens by themselves are going to do the addition reactions, and knowing that we're going through the anti-mechanism. So it's a lot of just, can you group the reagents into their general reactivities to know what they do? So for the like SN1, SN2, E1, E2, it's a lot of nucleophile only. Those are our sulfur atoms and the conjugate bases of strong acids. The base only is going to be hydride in any of our bulky bases. The strong nucleophile strong base was those O minuses or N minus. And then the strong or C minus. And then for the weak nucleophile weak base, those were the neutral oxygen atoms. And so that was kind of how we sorted those for their relative nucleophilicity basicity. Then when we're looking at our alkene additions, the big hint is, do you see a pi bond at the beginning? So like, don't lose sight of which mechanism you have to do. Like, are we doing addition, substitution, elimination? By looking at, what am I starting with? If I start with a pi bond, I'm going to be doing addition. I'm going to be reacting with the pi bond. If I start with well, all of these are addition. Here, if I start with no pi bond or a good leaving group, then I'm probably doing substitution or elimination. If I see H nu, then that tells me radicals. And so then that's going to be either my radical hydrogen that we're abstracting, or doing the anti-Markovnikov addition with radicals. So pi bond, then you do the addition. No pi bond, you're just taking a CH bond. So it's a lot of just organizing the reagents, which is why I think it's really helpful to use your note card to keep all the reagents organized, to like make sure you know when you see this reagent, this is how it behaves. It behaves as a nucleophile, an electrophile, an acid, a base, an oxidant, reductant. If you can fit them into those categories, then that's going to make it a lot easier to know which reaction you need to do. For the ring openings with the anti-addition, when you're doing SN1 type for SN2. Okay, so that would be with the epoxides. So when we had our epoxides, if you had your strong base, so you're in base conditions, so you have like an alkoxide, then you're going to do an SN2 reaction. It truly just is SN2. You attack the less substituted side, so that you would end up with need some sort of solvent, and I don't have enough space. So let me move this label out here. Put in solvent so that this becomes an actual alcohol. So that was my true SN2. When I had acid, so this is base. So it was that O minus was strong nucleophile, strong base. That's going to do substitution right away. For, well, it's always substitution, but it's going to do SN2 right away. It's going to react right away. If you have strong acid, then we're going to protonate something. So that was where we had like sulfuric acid, and then you have some sort of weak nucleophile. So then that did our SN1 type mechanism. So that was where you ended up with, the you protonated your epoxide first, and then your nucleophile comes in and attacks the more substituted side, like an SM1 reaction would have. Like as if a carbocation had formed, which it doesn't, but if one did, then your nucleophile attacks that side. And the rationale behind it is because when you get this positive charge here, that's going to lengthen this bond, because all of these inductive forces are going to be pushing that oxygen farther away. So it pushes that oxygen out, and that's going to make it more readily open on that side. This is the same premise that we see because we go through that positively charged three-membered ring. That this is doing the same sort of reactivity as our anti-mechanisms. So that when we saw those like bromonium ion intermediate or whatever, we see that three-membered ring with the positive charge, it did the same thing, that it was still doing that SN1 type ring opening, just as like our protonated epoxides did, because it's the three-membered ring with the positive charge. So now we're going to have the inductive forces are pushing this away, making this bond longer. And remember, the longer the bond, the weaker the bond is. So it's actually more like this, so that is the side that the nucleophile attacks from. So that's why we're always opening those anti-additions on the more substituted side. Does that make more sense? Did I actually answer your question, Carter? Because I was kind of guessing what you meant. Because basically with the, okay, good. Yeah, because with the anti-additions, we're not doing SN2. We're only doing the SN1 type with the anti-additions. Cool. Oh, I also see someone wanted 28B. So while we're on the page, let's do that one. All right. So this is, I see H new, that tells me radicals. So as soon as I see that, I don't know why looks like the nu is an exponent. That's a weird formatting thing that Word must have messed up, but it's H nu radicals. So that is going to be, I need to have an initiation, a propagation, and a termination. Every single one must have it. You don't have to show them listed out like that, but I think it makes it a little bit easier just to make sure you have all of the steps. So if you wanted to, you can list it out. That's how I think I did it. Yeah, that's how I did it on the answer key, was that I actually like listed out like initiation. Here's an initiation step. Propagation. Here are my propagation steps. Termination. Here's my termination. You could also just have it react like a normal mechanism. So since the worked out steps are already on the answer key, I'm going to show you what I mean by you don't have to explicitly write the initiation, propagation, termination for the mechanism. So it's still going to be that same sort of thing of we're going to be breaking our weakest bond. The weakest bond is going to be with those radical initiators. Or yeah, so it's going to be the oxygen-oxygen bond or nitrogen-nitrogen bond. Like those are the ones that we're going to cleave, or halogen-halogen. Like we're looking for the heteroatoms that are going to be able to stabilize a radical when they split and be able to equally split them. So the initiation is just, we're splitting that peroxide, and you could use equilibrium arrows here, or forward arrows are a little bit more common, but you could use whatever one makes you happier. And we're going to end up with our two radicals. So then at this point, I'm going to bring in my hydrobromic acid, because this is going to be a strong acid, so it's going to be really reactive. Meaning it wants to react right away. So it is going to be the next thing that reacts with that first radical that forms. So we're going to get our first, so this is my initiation. So my first propagation step is where I get the OH taking the hydrogen off of the hydrobromic acid, and we're putting that one electron onto the bromine. This makes my bromine radical. So now that bromine radical is ready to react with my alkene. So we're going to have, well, that's an aggressive arrow. We got to make sure that we are making the most stable radical. That's why we're going to put the bromine on the end carbon and the radical in the middle. Also, I look at the product that I'm given, I need the bromine on the end. So when I do this step, I need to make sure that the bromine ends up on the end. So at this point, we get radical Br, and then we need to get hydrogen on this site. So we're going to have another one of those hydrobromic acids, making sure that one arrow is starting from the radical that exists, and then the other arrows start from the bond, showing where those single electron, where every individual electron is flowing. So this is another propagation step, because I'm going from another one electron to a different one electron. And that actually makes my desired product. But because this is a radical reaction, you must have a termination step. So we can't just stop here. Even though we made the thing that we wanted, every radical reaction must have a termination step. So it's just going to be reacted with any other radical. So it can be any radical species that existed at any point that this gets paired together. So I need to show how this thing gets formed, because that's what the instructions told me to do. And that's the product that we're given. So I got to show how this thing forms. But then for my termination, it's you literally pick any of them. So the one that I still have hanging out in solution is this OH. So that's why I thought, cool, have that one pair. It usually actually isn't going to be, this one doesn't really, like hydroxide radical and bromine radicals don't usually couple together. Like it's not going to form a stable product. But if you did any two radicals coming together. It could have been another Br dot because, you know, we kept making Br dots. So it's just any radical that existed at any point in the mechanism. You just need two of them to come together. So I used the other one that I still had hanging around, even though it didn't really make a stable product. I just needed to show that every radical reaction must have a termination step. So this is how you could show it doing like the, well, it's kind of snaking, but doing it without actually writing it out in list form. Okay. Any questions about that mechanism or radical mechanisms in general? One thing actually to note is if I had written this as one equivalent, you could still use HBr in this second step, even though you're using two of them, because we remember that there are billions upon billions upon billions of molecules around. But if I wrote one equivalent, I would have also been okay. And actually, even if I didn't, I still accepted it. Where if you just use that water that you formed, I was okay if you use that as your proton source. The better proton source when HBr is in excess is hydrobromic acid. But I was okay if you just showed me that you knew how to grab a hydrogen from somewhere, anywhere. Cool. All right. All right. So 26, anyone want 26? Yeah, we have A and D. Okay. All right, so we got to make sure that we are paying attention to the hints that we are given with those molecular formulas. So that's one thing. Make sure that we are writing the formula, writing whatever compound has that formula. So I'm going to do A first. So when I look at this, it helps, again, if you know what your reagents do. So what I see first is I see these two steps. So the thing that jumps out first to me is I see ozone. So that is going to cleave a double bond. So that is my alkene, the oxidative cleavage. I'm just gonna write oxidative cleavage. But what that tells me is at the end of step one, I need to make or have a carbon-carbon double bond. So because I need it in order to do step two. So either step one is going to be making the alkene, or I need to make sure that it doesn't touch the alkene so that step two can still react. Then for step three, I see that this is my reductive conditions. So that's what made sure that I had an aldehyde. So that's telling me that I need to have these two carbons originally connected in order to go into step two. So I have, if I make this 1, 2, 3, 4, 5, 6, that means that before step two, so here's step one, the product of step one needed to be, let's see, 1, 2, 3, 4, 5, 6. All right, between 1 and 6, I get my double bond. And then off of 1, I get my methyl. So I need this intermediate. This has to be the thing because that's what makes this product with my ozonolysis conditions. That's what's going to break open the ring because I see two carbonyls, and remember that that's what clicks them together. Or well, it's not clicking them together, it's actually breaking it apart. But when you're trying to do the retrosynthesis, you're like, whoop, turn them carbonyls onto each other, and that assembles your carbon scaffold. So that tells me, all right, cool. So I know that this has to be my starting material going into step two, meaning that this has to be my product of step one. So now I'm going to consider, okay, so for step one, I see strong acid a weak nucleophile, weak base, and heat, which is telling me I'm going to probably be doing an elimination reaction. And because I know I need to make that alkene, it's really looking like an acid catalyzed dehydration. So that acid catalyzed dehydration means that I would have started with an alcohol, and it's going to be via an E1 elimination. So I'm going to say, all right, to know where my alcohol had to be, either on carbon 1 or carbon 6, I'm going to consider both options. When I do step 1, because the left and the right side are equivalent, I get those two products. If I use this 2-methyl cyclohexanol, I get these two products. So what I see is that with this first option, because it's symmetrical, the two elimination products that I get are exactly the same molecule. So that's perfect. Whereas in the second one, it does give me one of the desired products, but it doesn't give me the, oh, that's a lie. It actually wouldn't do that. Because this would be the Hoffman elimination. And we don't do that. Because we always form our Zatsev product. Because we're doing E1. So actually symmetry here doesn't matter. What did I write? Oh yeah, I said you could do either one. Okay, good. Got worried for a second. So yeah, so because either one of them will lead to the desired product, then it doesn't matter which one you draw. So last thing we need to do is double check, does that molecular formula actually work? So one other indicator that I could have used that I need an alcohol was I saw oxygen. So that was really my hint that like, I'm probably not going to have like any other leaving group that I need to have oxygen around. So alcohol, aldehyde, ketone, couldn't be an ester. Ester needs 2 oxygens. Couldn't be carboxylic acid. That needs 2 oxygens. But seeing 1 oxygen, that tells me I am an alcohol, ether, a ketone, or aldehyde. All right, those are my only options that contain a single oxygen. Those are the functional groups that had a single oxygen. So those were the ones that we needed to be. So then we're going to say, all right, I need 7 carbons. 1, 2, 3, 4, 5, 6, 7. Checks out. 14 hydrogens. All right, so there are 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes. If I remembered my degree on saturation formula, I could have checked this to see that I needed a ring. And that would have reinforced the fact that it would have told me I need 1 on saturation, which would have told me either 1 pi bond or 1 ring. And the fact that I needed to have this be cyclic originally in order to do that oxidative cleavage, that's what really kind of told me the unsaturation had to be a ring, not a ketone or an aldehyde. So if you knew the unsaturation formula, that could have made it a little bit faster to predict it, but we could absolutely do it without it. And so then these will accurately create our desired product after doing that retrosynthesis, and it matches our formula, so we know that we are right. All right, I hope I didn't mess anyone up when I started doing the wrong E1 formula or product, but does anyone have any questions about that? All right. So for this one, when I look at this product, there isn't anything that immediately jumps out at me. So I'm like, I mean, I see I have to have an aldehyde. So I'm like, all right, if there's PCC, that makes an aldehyde. Or if I have What are the other ways we know how to make aldehydes? So this is where if you have your like reaction roadmap, that can help you because it's like, all right, what are all the ways I can make an aldehyde? We know that we can start from an alcohol, a primary alcohol with PCC. We can also have an alkyne, terminal alkyne, with our hydroboration oxidation. And that did the anti-Markovnikov addition that went through the enol, which readily tautomerized to the carbonyl. I don't think I taught you about dibol H, did I? I don't think I would have. All right, well, I mentioned it, so I'll tell you. I mean, if you want to use it, you could. You won't have any reason to, I don't think. I don't think there's any question where it'd be applicable, but you can turn carboxylic acids or esters into aldehydes with dibol H, which is diisobutyl aluminum hydride. So it's that thing. So it's a less reactive form of LH. Yeah, I don't think I taught you about that, but that makes aldehydes. I don't think you know of any other ways to make aldehydes. All right, well, these are our options then. So, and really, we're looking at these two. So when we look at our reagents, there is no PCC. So remember PCC, the full thing, which you need to know both the abbreviation and the full combination of reagents, is that chromium oxide, hydrochloric acid, and pyridine. And you can use the abbreviation for pyridine, that's fine. But it's pyridine. That's the poison. So since I don't see that, I know that I'm not going to turn an alcohol into an aldehyde. So my only option becomes, all right, well, I must be turning an alkyne into an aldehyde. And so when I look at these reagents, you might look at this thing and be like, what the is that? What is that? And what I want you to do every time you see reagents where you're like, I don't know what that is. And you have that moment where your brain might shut down because you're like, I've never seen that before. That's when I want you to remember, breathe and think. Because even though it's so easy to panic during an exam, and to be honest, if I saw that, I probably would have just skipped this question and come back to it at the end. Or I would have had it on my note card because I'm pretty sure it was in your homework. But even if it wasn't, it's like, okay, what does it look like? What do I, what is anything that I see that's similar? And it's like, I see boron. Okay. What are reagents that have boron in it? Well, we had our sodium borohydride and we had BH3. All right, so those are really the only boron reagents, or I guess you had BF3. So BF3 was a Lewis acid, which we saw back when we did acid-base chemistry. Sodium borohydride, that's our reductant. BH3, this did the syn addition. It was the electrophile that did the syn addition. And so then it's like, okay, the difference is that one has fluorines all over it. So that doesn't really look as similar. This boron, sodium borohydride, that has a negative charge. So not that one. And so then it's like, all right, well, then it must be similar to the BH3. So even though I don't really know what this is doing, it looks like BH3 kinda. So it'll probably react the same way. And when I look at the second step, I see that it does that oxidation in the second step that it would do normally if it was BH3. So the answer is, why is it this monstrosity? This part is really sterically encumbered. That helps improve your regioselectivity. With your terminal alkynes. So it's because it's really bulky, and sterics is what actually helped force the or actually is what forced that anti-Markovnikov regioselectivity. The boron went to the side where it can more easily access, and the hydrogen went to the more substituted side. That with BH3, because your alkyne is linear, you actually sometimes get a little bit of a mixture of products. So if you're like, I'm guaranteeing myself that I'm only going to get my terminal regioselectivity, or that I'm only going to get the boron on the end, you bulk it up. That makes sure that this whole thing has to go on the end of the alkyne. So then that's what's reinforcing that, like, okay, so why does it look like that? It's so that I can do my anti-Markovnikov regioselectivity really well. But it looked like BH3, so that's kind of the thought process to go through, to be like, I don't know what that is, but like, what does it look like? Like, let me think critically and try to think of what is something that I do know that might try to explain this. So this tells me, by knowing that this is what it is, that my product of step 2 has to be a terminal alkyne. And so this kind of checks out, because remember when we look at our sodomid, this is my extremely strong base. It also is a good nucleophile. But like when you see sodomid, I want you to immediately think base. Like that is an extremely strong base. So that is going to deprotonate. It's going to make pi bonds. So then when I look at this original starting material, I'm like, I see 2 halogens. Maybe this is that way that we did in order to make my alkynes. And I have a large excess. So that is going to help make the terminal alkyne, because you need at least 3 equivalents to make a terminal alkyne with sodomid. If you use terbutoxide, you can have 2 equivalents, but with sodomid, it must be 3 or more. You can have an excess. So that's kind of telling me, all right, I know that I'm going to have to make a terminal alkyne, and I think that this is going to do it. So then this water might not be obvious right away, but this is going to be a water workup, meaning that it's gentle. So I'm not going to do any sort of like acid catalyzed reactions. Like the other way of doing it would have been if you wrote HCl dilute. That would be the other way of like reinforcing that we're trying to be really careful to not do an addition reaction with hydrochloric acid, right? We just want to do a workup. We just want to protonate it to turn that carbon anion into CH. All right. So now we know everything that's happening. I still got to figure out where I'm putting all my carbons. So knowing that I have these reagents are going to put the aldehyde here. That means that this has to be my terminal alkyne. So my product going into step 3 has to actually have 2, 3, 4, 5, 6, all 6 carbons already set. And since step 1 and 2, they don't have any carbons in them. They're not adding carbons. They're just making pi bonds. That means that those are my 6 carbons, and I need this substitution pattern already installed. So I'm like, dope. All right, so I'm going to get 1, 2, 3, 4, 5, 6. Well, actually, let's maintain the same numbering. And so now I need to make sure that I exclusively make the terminal alkyne. So if you put both of your leaving groups here, you would risk making a mixture of your internal and terminal alkyne, that'll make a ketone. And really your internal alkyne is going to be the one that's more stable. So you make that product as your major product. Your desired product becomes the minor. So I don't want my two bromines on that internal carbon. So instead, you can put them on the end or do 1 and 1. And then that's what'll get you to this desired product. And your anion is always going to be the product of step 1 when you use that soda-mid. Any questions about D? All of 26. Did anyone want anything else in 26? No, I don't see any. Okay. Let's go to 25. Oh, 26B? Yeah, yeah. All right, cool. All right. So quick hint here is I see the words diene and dienophile. Diels-Alder. So that tells me that I need to make a 6-membered ring with the Diels-Alder reaction. So I'm going to say this is, I start at the alkene and then I walk over to be on either side to find my original diene. So I know that this is 1, 2, 3, 4. And now I have an issue of I could either go across to the right to make it 5, 6, or I could go up to make that 5, 6. I can do either disconnection. So I'm either making this my diene or dienophile, or this is my dienophile. So when I think of how I would split them, if I do, actually, let's do this. Okay. So this would give me, so here's 1, 2, 3, 4. And then I would need to have, those need to be syn, or cis, sorry. They need to be cis because there's cis in the product. So I need to make sure that they're still cis so that I retain that stereochemistry. Plus just ethene. So I'm going to draw my hydrogen so that it's more obvious what that is. So that's one option. Or if I do the other disconnection, so that this, sorry, meant to keep those same numbers. So it's 5, 6, and then, I made this 5, that's 6, and then I did this as 7, 8. Or I could have done 1, 2, 3, 4, and then made this 5, 6, 7, 8. All right. So if I'm doing now the red disconnection for those red numbers, then that says that this piece is my original diene. And the fact that it's a bicycle tells me that, like, in the Diels-Alder, you make 1 ring. So if it's a bicycle, 2 rings, you had to start with a ring, right? That's kind of our indicator of, like, you only make 1 ring from the Diels-Alder. So if it's a bicycle and you have multiple rings, you had to start with a ring to begin with. So we get that diene and this dienophile. again, must be cis because the stereochemistry or dienophile must be the same stereochemistry you get in your product. So then now the question becomes, all right, so which is the better answer? Because both are possible. This is where we have to remember our diene is our nucleophile, our dienophile is our electrophile. So we wanted electron withdrawing groups on our dienophile. So that's why having that nitrile, remembering that CN is carbon triple bond nitrogen, this is an electron withdrawing group. That's going to make this dienophile react faster. So this is the correct answer. This is the good, fast reaction to make that product. This is going to be the wrong disconnection because this is actually slowing down your both your diene and your dienophile, whereas this is speeding up your diene and your dienophile. So the easiest thing to do is always start with at the double bond, walk one away for each side, and know that those are your original 4 carbons. So I'll keep these. Sorry, I forgot to do the numbering. 1, 2, 3, 4. And then with the red numbers, this was 5, 6. And then this is red 7, 8. Any questions about B?
How do you know that the CN is like an electron withdrawing group?
Yeah, so I know it's an electron withdrawing group for 2 reasons. One, I see that electronegative atom, so I know that there's a dipole pulling electron density away. So I know that the polar bond is pulling out. Also, it's going to be an electron withdrawing group via resonance. So when I draw resonance structures, I get resonance structures where I get a positive charge on the carbon that's going to be cyclizing. So then that's what's telling me that it's a withdrawing group both via induction and resonance. So it's that polar pi bond pulling the electron density away. Any other questions about B? 25D is next. Yeah, our proposed synthesis. Okay, so this was meant to be a hint for this, is that you had to find a way to make your alkyne become an aldehyde. So it's like, all right, if I need to make an aldehyde, I can make it from an alkyne. Was my hope that it would help you with the predict the starting material question. Or that if you recognize this, but you couldn't remember reagents, if you were able to figure this out, then my hope was that you would then be like, oh, here are reagents that I can use. So you could have just written these exactly up there, and that would have received full credit. But I also accepted it if you just did the regular BH3, that was fine. And H2O2. Here I did not require solvents unless it was necessary. So what I mean by unless they're necessary for desired reactivity, meaning if you're doing substitution or elimination, include a solvent. If you're doing addition, we didn't really talk about solvents. So unless your solvent is adding in, then I was cool if you didn't write it. Because basically, most of the time, you probably noticed I didn't give you solvents. And usually, most of these reactions are occurring with aprotic solvents, is usually the common solvent that you would use for the addition reactions. But I was cool if you didn't include a solvent. But you needed to have H2O2 and NaOH. Those were the reagents necessary for the reactivity in order to do that anti-Markovnikov addition. Because I get the oxygen on the less substituted side. So I'm going to go through that syn addition where the pi bond attacks the bromine, the electrons for the that BH bond comes down. And then my hydrogen peroxide does that reaction, which does anyone want to work through it? Sorry, I just started. Does anyone actually care about this mechanism? Yes, okay, all right. I figured you would, but then I was like, if you don't, I don't like, I don't know, whatever. Anyway. So it's, well, I also skipped a step. So for the hydrogen peroxide, remember that the first thing that's happening is that we are deprotonating. That's what makes that nucleophilic peroxide. So that is going to attack your boron. I started this in the world's smallest corner. And so now when we see this, I see that B anion, the boron with a negative charge, that's making that carbon nucleophilic. And because we are already in a basic condition, we're going to be able to have an OH be a leaving group. So we're going to see that our bond, we get that weird rearrangement where it is that carbon bromine bond is attacking the oxygen next door, kicking out that OH. So when if I number all my atoms, just to make sure I don't lose track of anything. I am connecting 3 to 5. I am breaking the 5, 6, and everything else comes along for the ride, stays exactly as is. So I am going, here's my 1, 2, 3. I'm connecting 3 to oxygen number 5. Oxygen number 5 is still connected to the boron. That I numbered 4. And then I kicked out that OH, that bond broke. That was my 6, 7. So that's the weird step that most people usually forget, is that how do I get the rearrangement to occur? And the idea is anytime you see that boron with a negative charge, thinking like, you know, sodium borohydride or whatever, it's actually going to be carbon is the more nucleophilic atom. So that's what's going to come over. Also, I need to have the carbon attached to an oxygen. So I got to find a way to make that happen. So that carbon attacks that oxygen, kicks out the OH. And we get here. So now the ending, we need, oh, since I was drawing a mechanism, I should have also shown plus water. That OH attacks the boron to just kick that out. And then now we do our tautomerization. So if it had been, if we're making an alcohol, then, and you could still make an alcohol. So actually, let's finish this because it would have been like a normal, if it was an alkene addition, you would have protonated it at this point. I was just trying to save space is why I was trying to cut corners. All right, we'll do the protonation. Get this alcohol for your enol. And then the enols are highly unstable. So they are going to tautomerize. And in basic conditions, the tautomerization mechanism is a little weird. As long as you show a reasonable set of arrows, I would accept anything. I'll normally only give you the acid one because that's the one that we talked about. But it's actually that we are deprotonating it again. And then picking up the proton from water to make the aldehyde. But the general idea is we need to, like when we did our enol, just as a point of comparison, if it was in acid, which is the one that I showed you, was that this was coming down, that attacked whatever our acid source was. And then we had like water, some sort of weak base, did the deprotonation. So it just looks a little weird here because it's in base. Any questions about any of that? You want anything else from 25? 25 C and B. And no one at the moment wanted A, but we'll see if anything changes. All right, for C. Yeah, C is like one of the hard questions. So, I always try to have something that's going to really kind of challenge you to think out of the box. So things that I was hoping you would see here is I see that I have to make a cyclohexene ring. So I see, I mean, there are two double bonds, but I'm thinking how to make like cyclohexene rings in general is going to be Diels older. So that was my hope, is that you would have thought, okay, if I disconnect it here, that's going to be what lets me set this stereo center. Like I see this increased complexity all of a sudden to make this really complicated ring where I have a set stereo center and I am taking a very small molecule, suddenly making it very complex. The other thing that I was hoping is that you would see your two halogens. What we did with whenever we had the dihalogenated reagent, what we did when we reacted with that was we made alkynes. Like that's really when we used that precursor. So my hope is that you would think, how the heck can I make something really complicated? Okay, well, if I got to make a ring, the ways that we talked about rings were intramolecular reactions, which I don't see any heteroatoms here. So I don't see any way that an oxygen could reach down. Like it didn't make a cyclic ether. It made a carbon ring. Well, the only way we talked about making carbon rings was cyclopropanation, the 3-membered ring, not this. But to make a 6-membered carbon ring was Diels-Alder. So I was trying to think, okay, well, my retrosynthesis is going to be that I'm going to try to get this and this as my precursors to that. Because these are going to be what gives me this bond disconnection. Because remember, that's how we got this double bond on the electrophile side, was we retained it because only one pi bond reacts. So it would have been whoop, whoop, whoop. So you only react with one pi bond on the electrophile side. So you retain that other pi bond. So that was the hope, is that you kind of would have worked, you would have needed to do both a forward and a retrosynthesis to kind of think about it. Is, okay, I only know how to make really complicated carbon rings from the Diels-Alder. So I'm praying that the Diels-Alder works. And then the only thing that I really talked about with these two electron withdrawing groups was doing an elimination, was to make my alkyne, which when I think about the alkyne being like, oh, if this is an alkyne, that does work for the Diels-Alder. So then I'm like, all right, if I do sodamide as my first step, which remember, I need to have it in excess. So I assumed everything is in excess unless you tell me otherwise. So I'm assuming you have an excess. So you didn't need to write excess. But if you wrote 2 equivalents or 1 equivalent, that was wrong, because you needed 3 or more to make that anion. So this is going to make this part of it. So then the question becomes, okay, how do I add that carbon on? Well, instead of doing an acid workup to make this neutral, because I need to add this other carbon, let's just do an SN2 reaction. Let's add methyl iodide to do an SN2. And then the last thing that I need is for the Diels-Alder, I need this diene and heat to add the rest of the carbons. So it was really hard for this one because I didn't give you a lot of the carbons to start with. You had to add all of the carbons, really. And so you couldn't really map onto the product. So this question really was testing your retrosynthetic ability, was really kind of the point of this question, which is really hard because it's like, you know, I didn't give you a lot of hints here. Any questions about 25C? All right. I know I said that there was another one that people wanted for 25. Was there? Maybe not. Wait. We have 25CD. We did that. 25D, 25D, 25C. Oh, okay. All right, cool. Now that I mentioned it, does anyone want A or B? If you do, change your mind, let me know. All right. 24s next. There are requests for 24. All right. So 24. We are providing all valid resonance structures, 2 points per structure, for the molecule below, using 1 point per each complete set of curved arrows. We are including all necessary formal charges. We're going to circle the major resonance contributor of the 3 structures you draw. So that's a hint to tell you, draw 3 structures. So you need to draw all 3 resonance structures. So with this, you have to think, all right, resonance, remember, are 3 model systems. We have that lone pair next to a pi bond. We have the positive charge next to a pi bond. And then we have a polar pi bond, where we said that if it's a polar pi bond, then it can pull electron density away towards the more electronegative atom. So we're going to try to map onto these, and we do 1 and 2 first. And then if I need to do 3, then I do 3. But I'm going to try to do 1 and 2 first. So when I look here, I start at, I see the negative charge. That's my quick indicator to be like, all right, I see a lone pair. And so then I go next door and I see that this is where the pi bond is. There is no pi bond here. So then I have to go there and there. Oh, sorry, real quick to go back to 25C. If you skip step 2, you don't have enough carbons. Step 2 is adding that other methyl on. So you can't do the reaction without step 2. So steps 1 and 3 would not be correct. It's not enough because you don't have enough carbons. Okay. We can go back to 25, but let's finish 24 since I already started it. All right, so 24, we see our model system. We see a lone pair next to a pi bond. So we're going to start at the electrons, push towards the pi bond, put the electrons onto that oxygen. We do our little resonance arrow, and we get nitrogen. Everything stays exactly where it was. Everything that wasn't touched stays put. And do I need to draw in all lone pairs or, no, I actually didn't even grade it if you didn't draw in lone pairs. So, we can ignore lone pairs. Cool. You can draw them in if you want. I'll draw them in just because I already started. Okay. So if you want to keep them there, dope. Helps you make sure you know your formal charges. All right. So that's the first resonance structure. So right now I've used those 3 atoms. All right. So those are done. That uses this model system, that 3-atom system. So now the question becomes, all right, well, I see a positive charge next to a pi bond. So then that means I'm going to have to use my next model system. So I'm going to go, all right, positive charge. I start at the pi bond and I push towards the positive charge. When I do this, I make a mistake that a lot of students made on the exam and lost points. What is wrong with this structure? Oh, yeah, I am missing a double bond. That's a good point. Yeah, just kidding. All right, that wasn't the error that I meant to make, but you absolutely are right. I did do that. So thank you for catching that. Yeah, nitrogen's exceeding its octet. So that's the like, you're absolutely right. I made 2 mistakes. But the error that I was trying to highlight is nitrogen can't make 5 bonds. Just like carbon, just like oxygen, just like fluorine, any period 2 element cannot exceed its octet. It is impossible. It does not have the orbitals to allow it. It can't do it. So this is no. This is sad. This is sad face. That's a sad nitrogen. That nitrogen is crying. It can't handle all that electron density. So when we are exceeding our atom's octet, that means I need to have another arrow pushing the electron density away. So I use that same model system to recognize, all right, I had a double bond next to a positive charge, but I can't exceed that nitrogen's octet, so I needed a second arrow. So that brings me to the other correct resonance structure. With the other pi bond that I didn't forget this time, where now I get the negative charges on both oxygens and the positive charges on both nitrogens. On the nitrogen and the carbon. And then, so now I've used these 3 atoms. Well, I still see another pi bond. So I know I'm not done yet. Also, I told you draw 3 structures. So I also know I'm not done yet. So then the next thing that I'm going to do is start at that pi bond, that last pi bond, push towards the positive charge. And I get this last resonance structure. So it was 2 points for drawing each of these 3 structures, 1 point for each of these correct arrows. And if you had started, if you started with the positive charge pushing towards the nitrogen first, that would have been okay. but it usually meant that you didn't recognize the major resonance contributor. So it's usually best to start where you have the greatest concentration of electron density. Like you really want to do that first. Like start where you have electron density and push away from it. The curved arrows start where you have electrons, go to where you don't. Then consider the positive charge one, and then consider that. Yeah, so, okay, so then when we're thinking of the good resonance contributors, the ones that are good, even though nitro groups make it look a little weird, because you probably saw this and had this gut reaction of like, why are there all of these positive charges and negative charge? Like, there's so many formal charges. Also, where this carbon doesn't have a complete octet. So this, you're absolutely right. This seems to violate what I taught you back with exam 1. The answer is that because it's in conjugation, these are other resonance structures. And because I told you to draw 3, which is actually why I included the number in this question, was to make sure that you kept going to illustrate to me that you see that this pi bond is in conjugation with the rest of the system. So you're right. These are definitely not going to be major resonance contributors. These are very minor, very, very minor, very insignificant, because 1, we do not have complete octets, and 2, we have a massive number of formal charges. So we do have the positive charges on the less electronegative atoms and the negative on the more electronegative atoms. So we did that, but you're absolutely right. We didn't achieve complete octets. We violated the octet rule, and we are creating a massive number of formal charges. So what I was hoping is that everyone would see this good one, that this is really, that is the major resonance contributor. This is the good structure. That's the one you should circle. And because I told you draw 3, it would be, okay, well then what are the other reasonable resonance structures? What are the other possibilities? And it's going to be the fact that you have that double bond next to the like it's all in conjugation. So these are not great, but they do still exist. They are still possible. So that's why I wanted, like, I included the 3 structures, because if I just said draw all good resonance structures, then it would have been absolutely reasonable for you to just draw this one and ignore the fact that this is in conjugation. So there will be some resonance withdrawing effect. So this is something that, like, I don't have a great explanation as to why our structures are okay with this, but when you have a nitro group, the nitro group will withdraw via, and this is a nitro group in case anyone doesn't remember. It is both an electron withdrawing group via induction and resonance. So it really does do this. So why is it okay with it? I don't have a good explanation other than I just know it does. Like, this is what we see, is we actually see the hybrid. And yeah, I can absolutely draw the hybrid for that. So that's why I told you the number of resonance structures was because it would have been absolutely reasonable for you to not immediately recognize that the nitro group is also going to be participating in resonance because of, again, we violate the octet rule by whatever. 6 valence electrons, not full octet. And lots of formal charges. And that's why they are minors, but they do still exist. So the resonance hybrid. So I'm sorry, I'm keep talking because I feel really bad because I want to give you like a better explanation, and I don't know what it is other than it does it. Like when we study it, we see that it does do this. It behaves in this way. It's what the nitro group does. So a resonance hybrid. Okay. So for the hybrids, remember that anywhere where a pi bond moves, we're going to see the dotted lines. So we're going to draw in our core scaffold first. So I get my nitrogen, the oxygen, oxygen, carbon, 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 carbon. All right, so we draw in all of the core part of the scaffold first. Then Anywhere where you see a formal charge in every structure, it retains that formal charge. Actually, why am I starting with charges? Whatever, I started with charges. We'll start with charges. No, that's silly. We're gonna start with dotted lines. So anywhere where the pi bond moved, so anywhere where you see a pi bond in some but not all. So like I see a pi bond here, but it's not here. I see a pi bond here, but not here. I see a pi bond here, but not here. There's one there, but not there. There's there, but not there. And there, but not there. So like anywhere where you see a pi bond in some but not all, you put dotted lines. To illustrate that each of these bonds are essentially 1.5 bonds, right? I think that's how it works out, what the bond order would be. So it's, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. Oh wait, that's wrong. That was the wrong structure to count on because that was the bad structure. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, that is 9. Yeah, that works. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 9 divided by 1, 2, 3, 4, 5, 6. So that equals, oh, 1 1/3. All right, so each bond is about 1 1/3 bonds is the bond order, in case anyone remembers that from Gen Chem. If you don't, I don't blame you. I only remember because I just taught it. So we get dotted lines everywhere where we see those pi bonds moved. And then anywhere where the charge is the same in every single structure, it keeps that full formal charge. Anywhere where you see the formal charge in some but not all, it becomes a partial charge. So I see a negative charge on this oxygen, but not this one. So then that becomes a partial negative. I see a negative charge on that oxygen, but not that one. So the oxygen becomes a partial negative. I see a positive charge on this carbon, but not there. So that becomes a partial positive. And I see the positive charge there, but not there. So that becomes the partial positive. So this would be my resonance hybrid. And when we see the reactivity of like, what does this conjugate system do? It really is your new nucleophile would be attacking to one of those two carbons when they do conjugate addition. So, and if you're using this for the Diels-Alder, which although this would be a very sad dying, because it's electron deficient, that your nucleophilic site would be there and your electrophilic side would be there. So your arrows would come there, there, there. So there, there, there. Because the resonance effect does exist. It's just what we observe when it reacts chemically and when we calculate like relative bond lengths and everything. Any other questions about 24? Or resonance or anything like that? That was a good one to show a resonance hybrid on. I like that. Kind of brings in every aspect of the resonance hybrid. All right. Oh, that's right. The number, I had so much issue. Word hated me because like we missed, like there's no 21 to 23. And I think there's like numbers repeat. Oh, and I'm missing 8 through 16. And yeah, the numbering was all sorts of messed up as well. Okay. So question 20. Did anyone want 20? Oh, the next one that I'm seeing are 17, 18, and 19. Oh, yes, 20. Okay. All right. All right. So planar conformation. Remember that planar is flat. So that means that I'm going to draw I might as well do it in here. I'm drawing it as a hexagon. That's what planar tells me. So then the other thing I need to remember is that up equals wedge or wedge equals up. dash equals down. So this one wasn't numbered, so you could have done any of your own numbering, could have rotated it however you wanted. But what we recognize is this bromine is down axial. This methyl is down equatorial. This tert-butyl is up axial. So then the bromine is going to be on a dash, the methyl is on a dash, the tert-butyl is on a wedge. When I do the numbering, if I number this 1, 2, 3, 4, 5, 6, for the IUPAC numbering, then I like making number 1 up here. So I'm gonna do 1 up there and then go clockwise. It's my structure. I can do it however I want. You could put 1 at the bottom and gone counterclockwise or on the left or wherever you want it. It's your structure. I didn't give you a scaffold to start with. So I think on the first exam I did to force you to track like this carbon goes there. If I don't give that to you, then you can draw it however you want. As long as it's flat. So then you can number it however you want. I guess that's what I should say. All right, so carbon 1 has the bromine that's down, so it needs to be a dashed bromine. Carbon 2 has the methyl, again, down, so that's dashed. And then the tert-butyl on 4 is up, so it's wedged. So that's my planar conformation. And then I'm told to draw the exact chair flip. So that means I can't rotate the structure. I need to do the exact chair flip. So remember that with our chair flips, the farthest left stays farthest left. The farthest right stays farthest right. So I'm just pinching those 2 corners and shifting it. So since my general scaffold originally is going that way, my chair flip needs to go this way. So instead of it being like upper left to lower right, it needs to be lower left to upper right. And then we get our 3 sets of parallel lines. The farthest left stayed farthest left. So this carbon is this carbon. Farthest right stays farthest right. So this carbon is carbon 5. This is 2. And then remember that my numbering is going across the back, or you could say I'm going clockwise. So I need to go clockwise or across the back to finish my numbering. So that's 3. This is 4. That's 5. This is 6. No. This is 1. Yeah, that works. Yeah, I didn't actually start at 1. So then, and for our chair flip, up stays up, down stays down. But what does change is axial goes to equatorial and equatorial goes to axial. So when I go to carbon 1, this bromine is down axial. So it needs to become down equatorial. So when I look here for carbon 1, remember that the equatorial position is going to be parallel to 2 bonds away. So that means it's not one of these, it's 1 away. So it's going to be parallel to here, so it goes there. Or if you just remember the middle is always going to be parallel to the outside, then that works too. So it had to be this direction. If you drew it out this way, that is wrong. It had to be parallel to 2 bonds away. So that's my down equatorial. Carbon 2 needs to be down methyl. So that methyl becomes axial because the down equatorial goes to down axial. My up axial goes to up equatorial on carbon 4. So I find here's carbon 4. My up equatorial is again parallel. I need that 4 on the other side. I need it to be parallel to 2 bonds away. So my tert-butyl goes there. So then to know which one is going to be more stable, that's going to be, well, your large groups want to be equatorial. So the more stable is large groups equatorial. For your more stable, so my largest group is that tert-butyl. So I want the one where the tert-butyl is equatorial, not axial. That is my chair flip. Any questions about 20 or chair conformations or anything like that? So equatorial is always parallel to 2 bonds away. That's how it is when it's when you have everything in the tetrahedral conformation, because everything is tetrahedral. Like all of your equatorial positions are always parallel to 2 bonds away. That's how we draw our chairs. It's how it exists. $19. All right, we have 3 questions related to that structure. All right, how many unhybridized p orbitals are there? All right, so there are 2 ways of doing this. Remembering they are unhybridized p orbitals, they're what make our pi bonds. So every pi bond is coming from the side-on overlap of 2 unhybridized p orbitals. So each pi bond equals 2. The other thing is that we also need to keep in mind that lone pairs in resonance is going to be in 1 p orbital as well. So I need to either just count all the pi bonds and then look to see if I have any lone pairs in resonance, and then count like 2 plus 2. And then if there's resonance, which there isn't, because this lone pair is on the double bond, not next to it. I mean, there is resonance, but not with the lone pair. Then that's what tells me, all right, there are 4 unhybridized p orbitals. I could also identify the hybridization, because if I am sp2 hybridized, that means that there's 1 unhybridized p orbital. If I am sp, then that means that I have 2 unhybridized p orbitals. So if I assign the hybridization for every atom, then that can also tell me, because then I'm essentially just counting all of the sp2s and then double counting the sps. So I see that there are 4 single bonds, that is sp3. 4 single bonds, sp3. 4 single bonds, sp3. 4 single bonds, sp3. I have 3 regions of electron density, so that is going to be sp2, or double bond sp2. So this is sp2, sp2, and sp2. So I can verify for myself that these are the only sp2 hybridized, or rather, well, I know I just verified that those are the only sp2 hybridized atoms, but I can verify that those lone pairs are not in resonance by doing a full analysis of the orbital assignment of that oxygen. So if that oxygen is sp2 hybridized, that means I get 3 sp2 hybridized orbitals, because 1 plus 2 is 3, or the same number you put in is how many you get out. So I'm taking that, if I always start with 1s and 3 p's because of the m sub l values. That's how I get my 3 in, 3 out, plus that 1 unhybridized p orbital stays there. So remember, the only way to get a pi bond is to use that p orbital. Your sigma bonds have to come from the hybridized orbitals, and then your lone pairs get whatever's left over. There is no resonance if you're in an sp2 hybridized orbital. Resonance is only in your unhybridized p orbitals. It's only delocalization of electron density through unhybridized p orbitals. So it really is just 4 unhybridized p orbitals. All right, how many chiral atoms are there? All right, so I'm going to be looking only at my sp3, because chirality does not exist on sp2 or sp. You must be sp3 hybridized in order to be chiral. And so I'm going to be looking for a carbon that has 4 different things attached. So my CH2s and my CH3, they cannot be chiral. So then the question becomes, all right, well, what about this carbon? Well, what are the 4 things attached to that carbon? I see a methyl, a hydrogen, the top of the ring, and the bottom, I guess, the right side of the ring. And these are not the same. No symmetry. So that is a chiral carbon. That is my 1 chiral carbon right there. There are 4 different things attached to it. So then how many stereoisomers are possible? Well, you could remember your formula for counting your stereoisomers is equal to 2 to the n, where n is the number of chiral centers. So that's saying that you have 2 to the 1 which is 2. Or if you don't remember that formula, which I don't blame you, you just think about, okay, well, what are the 2 options for that line? Wedge and dash. Those are 2. Or you think of it as R and S. Those are my 2 options. Any questions about 19? Sorry, I realized the time, so I'm double checking my schedule of when my next meeting is. Okay. Yeah, okay, cool. We can keep going. Yeah, bear with me 1 second. I'm gonna pause the. Okay. All right, we left off. Thank you for your patience. Sorry, I just had to respond to that email first. All right. 18. Yeah, all right. So which diene is going to react the fastest? All right, so things we need to remember about our dienes with the Diels-Alder reaction. 1, they're going to be our nucleophile. Meaning that the more electron rich is going to be faster. Also, they must be S-cis, not cis, because we're not just talking about the stereochemistry of the alkene. It must be S-cis, meaning that they need to be on the same side of that sigma bond. So be careful with that. So then when we are ranking the reactivity, I'm going to see that the ones that are going to be fastest are the ones that are locked S-cis. So they're in the ring, so there's no free rotation. So that means that this is going to be either 1 or 2, and this is 1 or 2. The one that is locked S-trans, so there's no way to have that rotation, that is going to be the absolute slowest because there is no reaction. That diene does not react. So then that means that these have to be either 3 or 4 because they can rotate into be S-cis from the S-trans. S-trans is more stable, but they can rotate into the S-cis. So it's going to be slower because they have to rotate, but they can do it, so they will still react. So then to pick between these, now that I've considered the S-cis conformation, now I'm going to consider the nucleophilicity of them, having those substituents. So remember that electron donating groups are what we're looking for. And resonance is going to be stronger than induction. So if there's any electron donating groups via resonance, those will react faster than just via induction. When we look here, I don't see any lone pairs of electrons in conjugation. So there is no resonance. All I'm looking at is inductive effects. So for the inductive effects, I'm just looking for more substituted alkenes. So here I see that these alkenes are tri-substituted, whereas here they're just di-substituted. So that's going to be faster. And then for this one, I see that this one is di-substituted, whereas this is mono. So that becomes, that's faster. Cool. Any questions about that? So regrades on the final exam. There will be eligible, so you will be eligible for a regrade on the final exam. You are given, what's it say in the syllabus? I believe it's 60 days from the day of the grade assignment being posted. So no grade changes for anything other than the final exam or students with incompletes will be made after 11:59 p.m. on December 8th. Oh, that was a typo. That was supposed to be 5th. Cool, you get extra time. And then your final grade is going to be considered your grade is considered final, meaning nothing is eligible for regrade after 60 days from the grade being posted. So I haven't done the math on that. That's just the department policy. So assuming that your final grades are posted, I'll just assume by the 12th to be conservative. Then that's what is 60 days? How many weeks are that? 8.5 weeks. So then it's 1, 2, 3, 4, 5, 6, 7, 8. So we're looking at like February 7th is the last day that you'll be able to request a regrade for the final exam. You will not be able to request a regrade for any assignment after Sunday, because I had that typo. But really it should be today because we're gonna start processing the grades. So unless you notify me, like you got to notify me right away if there's any sort of errors or anything, like submit the request by today as an email. I have my email is currently sitting at 700 emails that I have. So it's always a massive influx right at the end of the semester. So I'm trying to get through them as quickly as I can. But I will make sure that as long as your request is submitted, it will still be honored. And then for the final exam, because you have until that first week in February, you can request the grade change later. So how that applies or how that works is your grade will still be submitted to the registrar. If you request a regrade on your final exam next semester, then it will be regraded. If the regrade on the final exam alters your final exam grade, either by increasing or decreasing it, because remember, it can go down. So either increasing or decreasing your final exam grade, then we submit a grade change to the registrar and the registrar updates your grade. So you will still see a final letter grade submitted on your transcript, and then we will change it if you request a regrade on the final exam and find that there is something. Does that make sense as to how the final exam regrades are going to work? Like you don't have to do it right away. You can do it over like you can do it after winter break. Are there any other questions about the grading? Cool. Thank you. What makes it locked? Yeah, so locked is saying that there's no free rotation. So because it's in a ring, I can't rotate this, right? So if I try to rotate this so that it is S trans, so each of these rings are still cis conformation. So that means that 5 is over here and 6 is over here. So then I need to somehow connect these carbons. They're too far away. They can't. So that's why it's a locked S cis, meaning you can't rotate that bond because it will break the ring. So because it's in a ring, it stays there. It can't change. So same thing with this one and this one is that there's no way to rotate this and have the ring still be formed. So that's the locked, is that it's in a ring. Does the carbonyl portion of a carboxylic acid count as the backbone or part of the functional group? Yeah, let's do 17. Okay. So for 17, we're gonna draw the structure with the correct stereochemistry. So when we look at this, I see oic acid. That tells me carboxylic acid. That "and" tells me all single bonds. Oct tells me that I have 8 carbons in my backbone. So I'm going to start by drawing in the 8 carbons of the backbone. Oops. 1, 2, 3, 4, 5, 6, 7, 8. And because this is my structure, I can put carbon 1 wherever I want. So I'm going to go left to right because that's how I normally do it. So I'm going to do 1, 2, 2, 3, 4, 5, 6, 7, 8. All right, so those are my 8 carbons. That takes care of 8 carbons with all single bonds in the backbone. That carboxylic acid is going to be on carbon 1. That gets assumed because no number is written. So then, and it has to be on an end because it's a terminal functional group, like the carbon chain doesn't continue. So it has to be on carbon 1. So to answer your question, that carbon is a part of the backbone because when you have it as the primary functional group, that is saying the primary functional group is modifying that backbone. So this is saying that I have a total of 8 carbons in my backbone with a carboxylic acid on carbon number 1. So I put my carboxylic acid on carbon number 1. Then I see that I have that YL tells me it's a substituent. Meth tells me it's 1 carbon. Di tells me I have 2 of them, and they are both located on carbon 7. So I'm going to go to carbon 7, and I'm going to draw 2 methyl groups. So that takes care of my 2 dimethyls, or my 2 methyls. Then I go and I see the methoxy is telling me that I am an S or an ether. So that's ether with a 1 carbon chain on it, and that is on carbon 3. So I go to carbon 3 and I draw OMe. Hydroxy is essentially the hydrogen is saying, or the oxy is still saying oxygen. Hydro is saying you have hydrogen on it. So it's an OH. So, and that is on carbon 4. So that takes care of those. And then I see my stereochemistry is the last part. So now I got to make sure that on carbon 3 and carbon 4, they are both S stereocenters. So for carbon 3, usually the easiest thing for me to do is I just pick what, like I pick one of the stereocenters, check it, and I see if it's right. If it's right, cool, leave it alone. If it's wrong, draw the other one. So I'm just gonna pick wedge. Why wedge? Well, because then my hydrogen is on the dash. So then I know I can do the clockwise, counterclockwise right away. So I usually default to just make it the wedge first. So I'm gonna say, all right, so here's 1, then this is gonna be 2, and this is 3. Because remember that when you're assigning priority, you go atom by atom. So we have carbon 2, carbon 4, hydrogen, and oxygen. So that's why I knew that this is priority 1, that is priority 4. So then between carbon 2 and carbon 4, carbon 2 has 2 hydrogens and carbon 1 attached to it. Carbon 4 has 1 hydrogen, carbon 5, and an oxygen attached to it. So that's how I knew that carbon 4 is going to be priority 2, carbon 3, or carbon 2 is priority 3. So when I connect 1 to 2 to 3, that is counterclockwise with the lowest priority on the dash. So that is S. So that worked out. I got lucky. So I'm going to do the same thing with the alcohol. So if it had been R, just to quickly clarify what I mean by then just flip it, is if this had been R, then all you got to do is, instead of it being a wedge, make it a dash, and that inverts your stereochemistry. For the alcohol, again, I'm just going to pick wedge, start there. So I see that this is 1, 2, 3. That is also counterclockwise, so that is also S. So that also works. So I assume your question about does the carbonyl carbon count in the backbone or not, is coming from our aldehydes. So remember that with your aldehydes, they are the only ones that get weird. Every other functional group, it is like the carbon is in the backbone. Like it's, or the carbon is a substituent. Like it's, you count the whole group, right? Like it's always, if it's here, the carbon's in the backbone. If it's here, the carbon is not in the backbone. And that location tells you. And the only one that's weird, actually that's not true, because ketones aren't that way. Because ketone is just the oxygen. Aldehydes are weird because they're the only ones that have two options for the prefix. So I was trying to make more generalizations, but I can't because they have their own naming rules. But aldehydes have the option as a secondary functional group. So only when they're a secondary functional group, because the primary functional group, the carbon's in the backbone. If you are here, your carbon is a part of that backbone, like that, without any exceptions. That's what it means to have it be listed on the end. So for the aldehydes, when it's a secondary functional group, we had two options. We had either formal or oxo. We had two prefix options. So for formal, that meant that I had the carbon a part of this name. So that is saying that I have carbon, oxygen, hydrogen. It's adding, the carbon is included in the prefix, meaning it's not in the backbone. Oxo is saying that I just have this double bond oxygen. Like that's all oxo is saying. That's why oxo is used for ketones. So that oxo just means carbonyl. So then carbon is in the backbone. Because it is not in the prefix. Because oxo just means O, whereas formal means the whole aldehyde. And aldehydes are the only ones that have this weird variation. Everything else had one prefix, one suffix, and it just was, you just had to know what the prefix and the suffix were. Cool. Any questions about naming? Awesome, good. Let's see, what other questions do we have? All right, so we did 17, so working backwards. Looks like just number 4, I think, is the only other one that was requested. So for number 4, looking at which of the following statements is true regarding the Diels-Alder reaction with an ester on the dienophile. So that means that you have some diene plus your dienophile with an ester. So then it's going to be, all right, well then we need to make sure the diene must be S-cis, because that is true always. That's the only way that it reacts. So that immediately takes out the S-trans. And then because the ester is an electron withdrawing group, that means that it wants to be endo. So electron withdrawing groups go endo. Electron donating groups are exo. So then it's going to be option A. Are there any other questions that we want to go over? I can hang out for another 24 minutes, so I'm happy to do any questions at all. If you want to talk about, yeah, we could do others on other exams as well. But yeah, all right, so looking at 5. So for number 5, we have, what is the relationship between these? All right, so it's kind of tricky. It's probably easiest if you make it plainer, or, well, at the very least, I'm going to number them. So I'm going to number my carbons. So the first thing that I do is I look for, do I have the same substituents? So I know that this is my Newman projection of a 6-membered ring. So that tracks. I see an alcohol, a chlorine, and an ethyl. I see an alcohol, a chlorine, and an ethyl. So right away, I know that they are going to be the same molecule. So I didn't give you an option for different molecule. So they're going to have some sort of relationship. So they're either going to be some sort of isomer or exactly the same molecule. So then we're going to have to figure out, all right, well, which of them are they? So the constitutional isomer is if I have different connectivity. Enantiomer is where I flip all of my stereocenters. Diastereomer is where I flip some of my stereocenters. So when I look at this, I'm going to start by numbering because I'm going to figure out the easiest thing to do is just look at, like, are they different connectivity? Because if different connectivity, I don't have to worry about enantiomers or diastereomers because it's just different connectivity and I'm done. It's just that constitutional isomer. So I'm going to start at my alcohol. Why? I don't know. It's on the left and I felt like it. So I'm going to say this is 1, 2, 3, because that's the dots are the front carbons. The circle becomes 4. 5 is in the middle. 6 is the other circle. So then I'm going to start from this alcohol carbon. That becomes 1 to maintain connectivity. So then I need to head towards the chlorine. So because I don't know that these are necessarily like the exact same structure. Like they don't have to be conformational, or they could be conformational isomers or whatever. Like I didn't ask about that. So I could have rotated it. It didn't have to be the exact Newman projection of the exact chair or whatever. I just need to head towards the chlorine to make sure that my numbering is going to be the same to know if I have the right connectivity, right? That's all I'm trying to do right now is just check connectivity. So I head towards the chlorine to get my 2, 3. I see 4, 5, 6. So I need to have an alcohol on carbon 1. Yes. Then I need to see a chlorine on carbon 3. Yes. And my ethyl on carbon 4. Yes. So right now I know that they are not constitutional isomers because they have the same connectivity. The alcohol's on 1, the chlorine on 3, the ethyl on 4. So now I need to check, all right, what about my stereochemistry? Have I inverted anything? So it's easiest if I think about it in terms of like up and down, because remember, up is a wedge. Down is the dash. And when we're flipping, it's saying that all of your wedges go to dashes, dash, go to wedge. So when I think about this alcohol that is down equatorial, because the up is axial, so that hydrogen is my up axial. So this is down equatorial. This chlorine is up axial. This ethyl is up equatorial. So actually, the up or the axial equatorial doesn't actually matter. All that matters is up or down. But just for extra review, I'm saying that. So then that means that for this alcohol, this is up, also axial. The chlorine is up axial, and this ethyl is up equatorial. So what I see is that my chlorines are both up, so they're both wedges. My ethyls are both up, so they're also both wedges. But my alcohol went from a dash to a wedge. So that makes them diastereomers because I flipped some, but not all. So then, that's how I knew that. When I'm looking at this, I can also have tried to just map this Newman projection onto this chair. And so when I look at this, I see this down flap is this down flap. So I'm looking down the carbon 3, carbon 4 bond and the carbon 1, carbon 6 bond. So here are my eyeballs. There's my body. So I'm looking down these bonds from the left side of the structure. And what I see is that that's where I see that, yeah, that chlorine and the ethyl are in the same place, but I see that that alcohol has flipped. So I flipped one, but not all. Okay. Number 6. All right, so looking at our stereochemistry with our rings, we see that these are cis because, well, we'll start here. For the diene and dienophile, you start at the alkene, that's 2 and 3. You go 1 over, that gets you 1 and 4. So it means that this is my disconnect for my diene and my dienophile. So I see that these are cis. So I need my dienophile, sorry, to also be cis. So then the correct answer is D, because that's the only one that's cis. It couldn't be the alkyne because I don't have a pi bond here. So the alkyne eliminates option C and B. And then for A, the problem there is that that's trans. So I could solve all of this by just looking at my dienophile, but I can also look at the diene and recognize that my inside becomes the wedge, my outside becomes the dash. So that also checks out. Meaning that this was a trans alkene and this was a cis alkene for the inside and outside. Any questions about 6 or Diels alter? So you can't, dienophiles cannot be rotated. So the problem, so remember that you're, just like with your rings, how they're locked, that this is a locked conformation. This is locked in a trans conformation. If I rotate it, like I can't spin that pi bond, because if I try to spin this, remember that my pi bond is made of those two, actually I'll draw it, those parallel unhybridized p orbitals. That's what makes that pi bond, right? So the second that I try to rotate it, that pi bond breaks because it parallel, I keep the pi bond. Now when it's perpendicular, that breaks my pi bond. So that means that there is no pi bond. So I can't rotate an alkene. You can never rotate an alkene. You can only rotate your sigma bonds. Only sigma bonds where you have head-on overlap. That's the only time you get free rotation. Anytime you get the side-on overlap with your pi bonds, there's no free rotation. You are a locked conformation. And then the only sigma bonds you can't rotate are rings. So that's why we get cis and trans are geometric isomers with alkenes and rings, because those are the locked conformations. One O, P, and Q. Okay. All right, so reductants, they're going to increase the number of bonds to hydrogen and or decrease the number of bonds to oxygen. So we're looking for something that is going to do that. Potassium permanganate, that is an oxidant. It has a lot of oxygens. It's going to be adding a lot of oxygens. So that is an oxidant. So it's definitely not that one. Methyl magnesium bromide, that is going to be a reductant. That is our Grignard. Our Grignards are able to act as reductants. Because they are usually with like your aldehyde or ketone, either one. And it's reducing the number of bonds to oxygen. So it's not actually increasing the number of bonds to hydrogen, but it's reducing the number of bonds to oxygen. So Grignards can be reductants. They can also be nucleophiles. They can also be bases, but they are also reductants. But it's definitely not potassium permanganate, because potassium permanganate is absolute, it's our strongest oxidant we know for this class. So then looking at oxidants, again, these are going to be the ones that are decreasing the number of bonds to hydrogen or increasing the number of bonds to oxygen, increasing that oxidation state. So for that, PCC, that is our weak oxidant. Sodium hydroxide is not an oxidant. It is just a nucleophile or base. It is not going, it's a strong nucleophile, strong base, but it is not an oxidant. So there might be some confusion because it is going to be like adding an oxygen bond, but it's not changing your oxidation state, right? So if I have like OMe and I add OH minus, I get an OH, right? So that is not actually changing the oxidation state of my carbon. So sodium hydroxide, strong base, strong nucleophile, it is not an oxidant. PCC is the obvious correct answer because it is an oxidant. That is the pyridinium chlorochromate. It's a weak oxidant. It was our weakest oxidant that we talked about. It turns the primary alcohols into aldehydes and our secondary alcohols into ketones, but still it is an oxidant nonetheless. It is increased in number of bonds to oxygen. Protic solvent. Protic solvent is wherever you get the hydrogen on an electronegative atom so that you can do essentially hydrogen bonding. So anytime you have like an OH or an SH, that's going to be a protic solvent. So tert-butanol. Absolutely. Protic solvent. I have that hydrogen that is delta positive. Dichloromethane. That's DCM. Instead of abbreviation, that's an aprotic solvent because the hydrogens are on carbon. So those are non-polar bonds. So they are not protic. I, J, K, and L. All right, so jumping up here. Take care of that afterwards. Okay. I, J, K, and L. So our most nucleophilic is, remember that your nucleophiles typically follow your base trends. So strong nucleophiles are usually strong bases. The strong bases, that follows your charge, atom, resonance, induction, and hybridization. The strong nucleophile will follow that with the exception that size matters. Right? So if you are bulky, like a bulky base, you're base only, you cannot be a nucleophile, right? You need to be a small atom to attack a carbon. So looking at these for the most nucleophilic, the one with the negative charge is going to be the better nucleophile because it's the stronger base. Most basic, they are both negatively charged. So I'm not looking at charge. I go to atom. I'm comparing nitrogen to oxygen. So for my atom, I want the less electronegative atom is going to be the better base because that's going to have the electrons farther away from the nucleus. It's also going to make it less stable, more reactive. So less electronegative is going to be the stronger base. Then, so this was negatively charged versus neutral. This is less electronegative. Base only. So then that means weak nucleophile. So that's where I see bulky. So our hydride or any bulky bases were base onlys. So that's why it's that tert-butoxide. Our sulfur anions, those are extremely strong nucleophiles. These are nucleophile only. So remember that nucleophile only, those are our sulfur, anything, neutral or anionic, and our conjugate bases of our strong acids, because those are highly polarized or would form a strong acid, so therefore a weak base. So nucleophile only, all right, then we're looking for conjugate base of a strong acid, NaCl. So still negatively charged, making a strong acid, or making it a strong nucleophile. And then it is going to not be a base because it makes hydrochloric acid. NaH, sodium hydride, is a base only. It's not even like a reductant or anything. It is a base only because it makes hydrogen gas. So it's going to do that acid-base reaction really quickly. Okay. And then for SN1, SN2, they are favored with cold temperature and room temperature. So we're saying that substitution is generally favored cold. So typically at room temperature, elimination will be favored. The complication becomes with SN1 versus E1. At room temperature, it's a little more ambiguous because both of their rates are based on just forming that carbocation. So usually an SN1 reaction still actually will occur at room temperature. But to make it a little bit easier, we had said that we're going to say substitution, cold, room temperature, heated, we'll say elimination. It is absolutely true for our concerted reactions. So if you're looking at SN2 versus E2, absolutely. There's no maybe, it really is that way, that cold, substitute SN2, room temperature, heated, E2. SN1 versus E1, that's where it gets a little ambiguous, but we're going to keep it easy and just say cold, SN1, room temperature, heated, E1. But technically, they both will happen at all three temperatures. Well, SN1 will happen at cold, room temp, and heated. All right. Headed back to 27. 27N. Helps if I know my alphabet. All right. So for this one, I see my diene. That's where I have the two carbon-carbon double bonds, the conjugated diene. So this is going to be my diene. This is my dienophile. And so I see that it is that pi bond. The ester is an electron withdrawing group via resonance. My methoxy is an electron donating group via resonance. My methyl is an electron donating group via induction. Resonance is the stronger factor, so I'm just going to consider the resonance when I think about my relative, like, reactivity or the regioselectivity. There we go. So I'm going to end up with a delta negative here because I'm going to get a resonance structure where I get the negative charge on that end carbon. So that means that that is my nucleophilic site. When I draw the resonance structures with the ester, that is my delta positive. So that means that I really am connecting these carbons as they are. This would have had to have been rotated to become the S-cis. But it has free rotation, so it can still rotate to do that. When it rotates, we still make sure that to show what that looks like. So when I rotate this to become S-cis, I look at the stereochemistry of this top alkene, and my oxygen is opposite of my carbon chain, so it's trans. So I need to maintain that stereochemistry when I rotate it. So essentially I'm just like flipping that bottom around. So then when we go to draw our product, we get our 6-membered ring, double bond between the 1 and 2, or sorry, between 2 and 3 for those carbons. Here, I'll actually number them. So then I get initially that dashed OME, because it is out. Yeah, outside. And then, is that right? Yeah, outside is dash. And then our alkyne reacts, so we keep a pi bond between 5 and 6 because we only used one of them. Off of 5, I get my methyl. Off of 6, I get my ester. And then it's plus the enantiomer. But in my instructions, I tell you, you can't just write plus enantiomer. You need to draw the enantiomer. So the enantiomer is, there's only one chiral center. So it's, I'm flipping this one. So that means I'm going to draw this again, but with the wedge. Or because there's only one chiral atom, we can actually just draw it just with a straight line. Yeah, so the reason why you get both wedge and dash for the methoxy is because you get that, like, this is your initial to try to make sure that you're getting the initial stereochemistry for your four contiguous stereocenters again. But then you get that plus the enantiomer. So we always still get that enantiomer as well, which is where you're flipping everything. But in this case, there's only one stereocenter to flip. So it's just the dash becomes a wedge. But if these had been wedges, then you would need to make sure that we couldn't just use lines. We would actually have to draw the dash wedge wedge and then wedge dash dash, right? So you would have to be cognizant of that. For the inside outside, yeah. So if you are outside, then we said that it is going to, we said outside, basically if you're trans relative to your central sigma bond, then you become a dash. If you are inside, meaning you're pointing towards the center of my diene, then that becomes a wedge. And then plus the enantiomer. Any other questions about N? Yeah, you're always going to get the enantiomer with it because you have, we have this planar starting materials. So anytime you're working with something that's planar, you're always going to create racemic mixtures. So yeah, just like how if anytime you make a carbocation, you get a racemic mixture. Same thing, because these are planar, you're going to get a mixture of enantiomers. Any other questions about N? There's one more. Let's do 27H. Oh, so going back to 27H, is it okay to draw the structure with the, yeah, sorry, okay, sorry. Before we start that. So the inside outside, yes, this is setting the stereochemistry relative to the stereochemistry of your diene, or your dienophile, sorry. So it's trying to set that relative stereochemistry. Yeah, that's absolutely right. So if you just remember as inside outside, that helps you remember where to start to get your first enantiomer, and then you just have to flip everything else. It's 100% correct. It's the relative to the other substituents. For H, I need to reread my instructions. So the question for H is it okay to draw the wedges and dashes? So is it okay to do either, oops, that or that. And it depends on the instructions. So what I'm gonna tell you right now is that neither of these are stereo centers. So having wedges and dashes is like not necessary. So we need to read the instructions to know if we're allowed to, basically. So it's not that this is inherently wrong. It's just not necessary. So the instructions are going to tell us, is it okay to show stereo, like to have wedges and dashes when I don't have a stereo center? Or can I only use wedges and dashes with stereochemistry? So what were my instructions? All right, so we're predicting the major organic product of each one. If the major organic products, if multiple are expected, draw all of them. If an organic salt is produced, you may omit the counter ion, but charges must be indicated. All right. Use wedges and dashes and or lines as necessary to correctly depict the stereochemistry. Okay, so then because we are trying to draw the correct stereochemistry, then you would need to use a line there to indicate the correct stereochemistry, rather indicating that there is no stereochemistry. So in that case, then these would be wrong for those instructions. Yeah, I'll just leave it as no stereochemistry. Any other last minute questions? So like for 25A, is that what you mean? How to turn? Yeah, okay. So it's going to be essentially the exact same thing that we're going to, oh wait, an alkyne into a ketone. So we'll do both, whatever. Okay, so if you're trying to get an alkyne into a ketone, so if I want that to become this, the alkyne, I need to remember, does the enol tautomerization. So it means that I need to make this intermediate because that readily becomes the ketone. So that means that I need to do a Markovnikov addition. So that would be anything like H2SO4 and water. Or you could do your HGSO4 or HGOAC2 and water. And then actually what's really kind of weird is that you technically actually don't need the sodium borohydride for some reason, but I don't think I told you that. So if you still write it, that would be fine. It just doesn't do anything. So these are our Markovnikov additions to add water, to add that OH. So if you're trying to turn it into a ketone, you need to make the Markovnikov enol, and then it tautomerizes. For 25A, we have our alkene. So there are a bunch of different ways we can turn that into a ketone. And the easiest thing is probably to, instead of trying to make it an alkyne first, which you could, so we could turn it into an alkyne first. So if I wanted to have an alkyne, if I brominate this, that gives me bromine on both sides, which I could then use. I'd want to use terbutoxide because I told that I can't have more than 3 steps. So I don't want to have to do an acid workup or anything. So I'd have to use the terbutoxide instead of sodamide to get my alkyne. And then I could do the hydration, whatever, in order to get my ketone. Or I could have add an alcohol, do the hydration first, add the oxygen first, doing the Markovnikov addition, either that or with the hydroboration, no, oxymercuration, demercuration. And then we just need to oxidize it. So this was hydration. So oxidation with either Jones or PCC. But again, making sure that we were writing the complete set of reagents. So you couldn't actually write Jones or PCC. Like you can't write the word. You'd have to write out chromium oxide, hydrochloric acid, and pyridine, or chromium oxide, sulfuric acid, and water. Right. If you still need to pick up a note card, you can come do that. I'll be in my office. I need to eat lunch really fast, but I'll be in my office from 12:30 to 1:15 today. So you can come pick up the note card. My office again is Evans Lab 1045. And then otherwise I will talk to you later. Right. Have a wonderful day. Bye.